Now we're going to take a look at chemical formulas as conversion factors in and of themselves. And let's look at what we mean by this. For example, if we're talking about a spider will have 8 legs. So if we have 8 legs, we have 1 spider. If we have 2 spiders, we have 16 legs. If we're talking about a chair, we're talking about 4 legs. And if we're talking about a water molecule, we have 2 hydrogen atoms. Just like the chair and the spider, molecules have specific ratios of the things that make them up. So 1 spider equivalent to 8 legs, 1 chair equivalent to 4 legs, 1 water molecule, 2 hydrogen atoms, and 1 oxygen atom. So for example, if we know that there are 30 desks in a room and each desk has 4 legs, there's going to be 120 legs total. 4 times 30. And if we know we have 100 water molecules, then there have to be 200 hydrogen atoms because each molecule has 2 hydrogen atoms. And likewise, if we're talking about a mole of water molecules, then there are 2 moles of hydrogen atoms. So let's look at some examples here of ionic and covalent compounds. Here's an ionic compound, since it has a metal in it. 1 mole of sodium chloride is going to have 1 mole of sodium and 1 mole of chlorine. 1 mole of water is going to have 2 moles of hydrogen and 1 mole of oxygen. 1 mole of calcium carbonate is going to have 1 mole of calcium, 1 mole of carbon, and 3 moles of oxygen. And 1 mole of glucose is going to have 6 moles of carbon, 12 moles of hydrogen, and 6 moles of oxygen. So let's look at this practice problem. Calculate the number of moles of oxygen in 1.7 moles of calcium carbonate. So I'm given 1.7 moles of calcium carbonate, and I want the moles of oxygen within this sample. So I'm going to use the formula to give me the conversion factor. 1 mole of calcium carbonate always has 3 moles of oxygen. And now I have 2 of each of my units. Moles of calcium carbonate, moles of calcium carbonate, moles of oxygen, moles of oxygen. And we can go ahead and do our railroad math. I'm given 1.7 moles of calcium carbonate. So I have to have calcium carbonate down here, moles of calcium carbonate. So here's my conversion factor right there. 1 mole of calcium carbonate always has 3 moles of oxygen. My units of moles of calcium carbonate cancel out, and I'm left with moles of oxygen, which is what I want. And then my final answer is 5.1 moles of oxygen. Does this make sense? For every mole of calcium carbonate, I have 3 times the amount of moles of oxygen. So yes, this makes sense. Now let's take it up a notch. Carvone, C10H14O, is the main component in spearmint oil. It has a pleasant odor and mint flavor. It is often added to chewing gum, liqueurs, I don't know how you say that, soaps, and perfumes. Find the mass of carbon in 55.4 grams of carvone. So let's look at what we're given and what we want. We're given a mass of this compound, and what we want is a mass of the element within this compound. So, let's see what we can do. We know that 1 mole of this chemical carvone has 10 moles of carbon. We know that based on the formula. Now we're given mass and we want mass, but our conversion factor is in moles. How can we get from moles to mass? The same way we always do molar mass. So I'm going to need the molar mass of carbone, and I'm going to need the molar mass of carbon. Go ahead and calculate the molar mass of carbone and see if we come up with the same answer. This is the molar mass that I came up with using the molar masses in the periodic table on the inside cover of your textbook. Now if I do a unit check, I have grams of carbone, moles of C10H14O or carbone, moles of C10H14O. But I only have 1 gram of carbon, and I also only have 1 mole of carbon. So I need one more conversion factor. 1 mole of carbon is equal to 12.01 grams of carbon. So if I do my unit check, grams of C10H14O, grams of C10H14O, moles of C10H14O, moles of C10H14O, grams of carbon, moles of carbon, moles of carbon. Now how did we get here? Well, we started out with what we knew. We knew that 1 mole of C10H14O was 10 moles of carbon. And then once we got here, we realized that we were given mass and we wanted mass. And our conversion factor was in moles. Anytime you're getting between moles and mass, you've always got to use your molar mass. And then we used our unit check to make sure we had 2 of each unit. Now we have what we need to do our math. We're going to go ahead and do our railroad math. So it's really important to clearly write everything down. Here we have grams of C10H14O. That is what must go down here. And here's the conversion factor that has grams of C10H14O. The other half that conversion factor is 1 mole. So now I have 1 mole of C10H14O, and so a mole of C10H14O is what goes down here. And then on top we have the other side of our conversion factor, 10 moles of carbon. Now notice we have 2 moles here, so we've got to clearly write down which chemical is which. Now before I go any further, I'm going to make sure my units cancel out. Grams of carbone, moles of carbone, moles of carbone. Okay, so far my units are canceling out, so I know I'm on the right track. And then here I have moles of carbon, so moles of carbon has to be on the bottom. Here's my last conversion factor here, and when I do that, I end up with the units I want, grams of carbon. So everything cancels out. I've used all my conversion factors, and now I'm going to let my calculator give me the answer. So my calculator tells me 44.286, and it goes on further, but I'm running out of room, and I know I'm only going to have 3 sig figs. So 44.3 grams of carbon. Okay, now let's look, does our answer make sense? Well, it's not larger than the original value. This is our total sample. And if we look at what the sample is made up of, it's mostly made up of carbon. It has 14 hydrogen atoms, but hydrogen is very, very light and has 1 oxygen. So yes, it makes sense that most of the mass of this molecule would come from carbon.